All right, so take a look at your 6.1. So everybody got the 6.1 looking at it. This is continuation of the last thing that you saw in Calculus 1. So you were doing at the end of Calculus 1 how to find the area under the curve. So what I'm going to just remind everybody of is the definite integral. So do we remember what that is? What is the definite integral? That's the thing that we said was this, right? What does the definite integral tell us? So you guys can answer, you can write. What does the definite integral tell us? Yeah, exactly, the area under the curve. So just to remind everybody, yeah, area under the curve between two x values. So basically, you have some function and you've got to define between two x values. Then the definite integral tells you that area there, right? Now we have to sort of qualify that, right? Because it doesn't always tell us the area under the curve, right? What if some of the function is below the x-axis? Well, if it is, then it's not going to tell us the area anymore, right? It's going to some of it is going to be negative, and so any negative portion is going to subtract from any of the positive parts, so it won't be an area at that point. However, if the function is entirely above the x-axis, then yes, it is going to give us the area. And so let's also just remember what the actual definition of that is. It was the limit as n goes to infinity of the sum from n equal 0 to infinity. Oh, I'm sorry, I'm doing that wrong. From I equal 1 to n of f of x sub I delta x. And really that delta x could also have a sub I on it as well, although we don't really have to do that. And so what that came from, if we remember from Calculus 1, that came from this notion where if you wanted to sort of approximate the area between two curves, what you would do is divide it up into some number of subintervals. I'm just going to use, let's see, 1 to 4 here, just so we can remember what that was doing. And so the idea was that if you had a curve like that, you could approximate it by either right or left endpoints. Suppose you use right endpoints, then you plug in the right endpoint of each subinterval, and then that produces the height of a particular rectangle, like that. And so then you've basically got 4 rectangles, and then you add up the areas of all of them. Each of them has a set width, right? There's delta x here. That's the delta x that's on the end of the definition there. And then the height of each one of these is determined again by whether you're plugging in a right endpoint or a left endpoint or some point in between them. Anyway, what do you do after all of that? Then you add up all these areas, right? So we have like area 1, area 2, etc. Add them all up. It gives you an approximation to the area. And then to get a better approximation, what do? You let this delta x shrink down, which then makes the number of rectangles get greater and greater. More rectangles you have, the better approximation that you have. And then eventually when you take the limit as n goes to infinity, then you get the exact area under the curve. Everybody remember that from Calculus 1? That was the definition, how we determined what that definite integral was going to be. Okay, cool. So any questions about that? All right, so what we're going to do now is look at how do you determine the area between two curves. So that's very similar to what we were just remembering from just finding the area under a single curve. What we do here is we now have, say, two functions, right? So maybe one of the functions is like this, maybe the other one's like this. This is the f of x function here, this is the g of x function here. And actually, let me do that like this. And so the idea here is that you would still divide this up into some number of subintervals, only now the rectangles are not going to go all the way down to the x-axis. The top bound of the rectangle is going to be the bigger function, the f of x function, if that is the bigger one. The bottom one is the smaller function, g of x function. And we still have this same width, delta x. We still call this thing some x value on the subinterval. We call that x sub I star, perhaps, because the star indicates that it could be any x value that's on that subinterval. Whatever that x value is, we're going to plug it into both functions. That's going to determine the top and the bottom bounds for that particular rectangle, which we're actually going to use this kind of rectangle kind of a lot, and we can call that thing a representative rectangle. So we will be using a lot of these things that are called representative rectangles. All right, so now what we can determine here is the height of the rectangle must be what? Well, whatever we plug in to that top function, f of x sub I star minus whatever we get when we plug in the bottom one into that g of x function. And so the height of that particular rectangle is determined by the top function minus the bottom one. The width is still the same, so basically the only difference that we have in this would be the area is now going to be the same sort of thing, the limit as n goes to infinity of the sum I equal 1 to n. Now we're going to have f of x sub I minus g of x sub I. And then all of this gets multiplied by the delta x. And so that gives us the area of a particular rectangle, the f of x minus g of x. Multiply that by delta x, it gets us the area of the rectangle. Summing them up gets you an approximation. Taking the limit as n goes to infinity gets you the exact value. And so this is looking an awful lot like the definition of the definite integral. And so we can just define this to be the formula to find the area between two curves. Okay, so there it is. That's how you do it. Find the area between two curves. Any questions about that? So if not, remember that it did matter before when we were talking about just finding the area under a curve. It did matter if some of the function was, say, above the x-axis and some was below, right? So does that matter here? Like, what if part of one of these functions was below the x-axis? Does that matter as far as finding the area between the two curves? Yeah. You want to? Do you have an opinion on that? Does it matter? Suppose that we have like this situation where maybe one of the functions is like this, the other one's like that. This formula is still going to give us the area between the two curves. Well, if you think about it, that's what the representative rectangle would look like in that situation, right? Part of it would be below the x-axis, and part of it would be above. Hold on just 1 second. Okay, so this is the function, this is the function. So if you think about what's happening here, if I take this positive value, the g the f of x function here would be that distance, right? Somebody has got their, just moves everybody here. I'm getting some feedback on that. This is okay. So this would be the f of x, right? This height here, f of x sub I would be that. And then this would be the g of x bit right here. But that would be negative, right? This distance right here, that would be negative. So what are we doing? We're taking a positive value, that distance right there, this one, minus a negative value, right? But what happens when you subtract a negative? Well, subtracting a negative is actually adding, right? And so what we're going to get from the formula would be f of x sub I minus g of x sub I would be this top part minus this bottom part. The minus a negative is going to be a positive. It's going to work, is what I'm saying there. It will also actually work even if both of the functions are entirely below the x-axis. So you can kind of see what would happen in that case. This is what our representative rectangle would look like here. Not so terrible. It would look like that, perhaps, right? Now the f of x function would still be the top function, so let's call that the f of x1. This is the g of x1. Now the f of x height is going to be this right here, right? This distance right here from here down to that point, and that's going to be a negative value, right? Because it's below the x-axis. And then the other one, the g of x, is going to be this height right here, but that's also a negative value. So what we're going to have is a larger negative value. I'm sorry, the f of x1 be first, right? So we're going to have a smaller negative value, f of x1 right here, this one, smaller negative value minus a larger negative value, right? But what happens when you subtract a negative again? It becomes positive, and since we are subtracting a larger negative value, we're going to end up with a positive answer. And in fact, that positive answer is going to be the height of that rectangle right there. So the point here is that this formula works for any situation, okay? Don't have to worry about if any of the functions are below the x-axis or anything like that. It's still going to work, okay? Make sense? So I'm going to clear this off unless anybody has any questions. Okay, so no questions. I'm going to clear that away. All right, so let's do an example. One on the worksheet. This is find the area between of the region bounded by this curve y equals 2 minus x squared and y equals x squared. So you'll notice on some of these, they're going to give you the bounds. They're going to say starting at this x value, ending at some other x value. On some of them, they're not going to give you the bounds. If they don't give you the bounds, then that means that the functions have to intersect each other, right? If they don't intersect each other, then there's no area to find. So you will either be given them as they are in this problem, or you won't. And if you're not, then you're going to have to find what they are. But that's not that bad, because if you want to find where two functions intersect each other, you just set them equal to each other and solve, right? And then they have to do that in at least two places in order for us to be able to do this. All right, so let's see. Usually it helps to graph these when you're trying to figure out what the area is going to be. Let's think about what these two functions would look like. 2 minus x squared, parabola opening down, y-intercept of 2, so it's going to come down like that. And then the other one is y equals x squared, it's a parabola opening up, so something like this. So this is y equals x squared, and this is y equals 2 minus x squared. Now they're telling us to find the area between these two curves between 0 and 1. That's why I started at the y-axis. And then up to 1, well, it turns out that they actually do intersect each other at 1. So if you plug 1 into both of these functions, right, if you plug 1 in there and there, you find that you get 1 in both situations, right? So that means this right here is actually the point of intersection. What we're looking for is this area right here then. That's what we're after. What is that area? Okay. And then, so how do we do that? Well, again, with this formula, you have to put the bigger function first. Bigger, by bigger, I mean like bigger y values on the interval. So like on this particular interval, this function here is the one that's higher up on the y-axis, right? So that's the one we would want to put first. So we'll put 2 minus x squared first, minus, so that's the f of x function, minus the other one, minus the g of x function. That's what we need to do then. That's the interval we have to find. Okay, so that, let's simplify it and then find the antiderivative. So this is 2 minus 2x squared. So that's the integral that we have to find. Again, you can kind of see, again, when I said you got to know how to do your calculus from calculus 1. Well, here we go, right? We got to remember how to do these integrals. So the antiderivative of 2x. The antiderivative of 2x squared, 2/3 x cubed. Plug in 0, plug in 1, subtract them. Well, if I plug in 1, I'm just going to get 2 minus 2/3. If I plug in 0, I'm just going to get 0. So that's it, right? So 6/3 minus 2/3 is 4/3. So 4/3 is the area between these two curves on that interval from 0 to 1. Okay, any questions about that one? All right, well, if not, we'll go on to the next one. Feel free to stop me if you do have any questions. I have a question you might be thinking. What if, or how do you tell which function is the bigger function on the interval? How do you tell? Well, you can either graph them, and that hopefully will make it obvious, or you could alternatively take any number that's on the interval, right? Like you could pick 1/2, say. And what if you plug that number into both functions? Well, the output of the bigger function will be bigger, right? And so that's what's going to tell you what the bigger function is. Plug in some number that's on the interval that you're given. Okay. Now, here's another question. Suppose that you get it backwards, right? And you mess it up and you put the wrong function first, and then you try to do the integral. Well, of course, you're going to get an answer, but what's your answer going to look like? Everybody follow what I'm saying? Suppose you put the wrong function first. Yeah, you're going to get the negative answer, but it's going to be the negative of the correct answer, right? So you, just to point this out, you will never get a negative answer on this problem if it's set up correctly. You'll never get a negative. So if you do get a negative, chances are that's what the problem was, that you have the functions switched. And in fact, if you want to, what you can do, like another way to view this formula is just to say, well, I don't care which function's first. I'm just going to say that the area between the two curves is defined like this. Right? You could do that. And if you want to do that, that's perfectly fine. You could just take the absolute value of the integral. Okay? So that's a way to around this, figuring out which function's bigger. Just say, I don't care which function's bigger. I'm just going to find the integral, put one function first, put the other one second. If it's negative, I'm just going to make it positive, and that'll be the answer. Okay. All right, so if there are no other questions, let's move on to the next problem. So I mentioned that sometimes they're not going to give you bounds, right? So take a look at this second problem. That's the situation we have here. Find the area of the region bounded by these two graphs, no bounds given. Okay, so we just have to figure out what those bounds are going to be. They have to intersect each other, otherwise this question wouldn't make any sense. If they don't intersect twice, then there's no area to find. Okay, so our first step here would be to find the points of intersection. So we just set the two functions equal to each other. We get x squared plus 2x minus 3, I guess. 0. So now we need to just solve that. So factor it, x, what is that going to be? Minus 1 and x plus 3, I guess. And so x is equal to 1, and x is equal to negative 3. Okay, now let's also go ahead and just try to graph it and make sure the graph kind of matches what we just found here. All right, so we've got x squared minus 1. We know that that's a parabola shifted down 1 unit, something like this. And 2 minus 2x. Yes, the question is, are we setting them equal to each other to find the bounds? Yes, that's exactly what we're doing. We're setting them up equal to each other to find the bounds. Okay, so notice that if you plug in minus 3 here, you're going to get, well, let's see, the other graph, what is it? It's 2 minus 2x, right? So that's a line. It's got a y-intercept of 2, and it's got a negative slope. So if I plug in, I don't know exactly, something like this. Right, so there's our 2 points of intersection, like that. Actually, I think even better. I think I have the graph a little bit wrong. I think it should probably be more like this. It actually crosses the x-axis right there, or something like that. Anyway, the graph isn't super important. I mean, it just kind of gives you an idea of like what are you expecting here. And my graph is certainly not particularly accurate because that's supposed to be minus 3 right there. And the other one's supposed to be 1. It looks something like that. Okay, cool. Yeah, if you have a calculator, of course, just put it on the calculator. That'll help. Okay. Anyway, that establishes the bounds. So now we know what the integral has to look like. And then the graph, it's pretty clear which function is the bigger one. The line is the one that's, got bigger y values. So we're going to go from minus 3 up to 1. The linear function is the bigger one on this interval anyway. And then when you subtract this other one, just be sure that you subtract the whole function. That's important. And that means you have parentheses around it. Okay, simplify the thing before you find the antiderivative. So we'll get negative x squared minus 2x, and then 2 minus negative 2 plus 1, that's 3, so plus 3. So that's the integral that we have to find. Okay, so we find our antiderivative, negative 1/3 x cubed minus x squared plus 3x evaluated between negative 1 and 3. So remember what that means. That means we have to plug in the top value, so negative 1/3. Multiplying that by 1 is just going to give us the number, so the coefficient. So we'll just say that, minus 1 plus 3. And then minus, what do we get when we plug in negative 3? Well, let's see, negative 3 to the third power is negative 27 divided by negative 3 is positive 9, I believe, right? So 9. When I plug in negative 3 to the next one, I'm going to have 9 as well, so minus 9. And then when I plug in negative 3 to the next one as well, I'm going to have a minus 9, right? So 9 minus 9 minus 9. Well, 9 minus 9 is a 0, so those are going to go away. We have a minus minus, so that's going to be a plus. So we got a 9, 10, 11, 12. Minus 1 is 11. So what is that? 11 minus 1/3. And that's 33 over 3. So 32 over 3. If I did all that correctly. Okay. Any questions? And if you see me make a mistake, please stop me. or tell me that I made a mistake, or that you think I did anyway.
So why did it get switched to like to a negative basically?
What gets switched to negative?
Oh yeah, so so instead of x squared plus 2x, it was negative x squared minus 2x. So how come it switched?
Yeah, so remember that in order to get that negative x squared minus 2x plus 3, how did we arrive at that in the first place? Well, we had to put the f of x function minus the g of x function, right? Well, what's the f of x function? It's the bigger function. So whatever function is considered to be the bigger one, that's the f of x function. If you want to think of it like that, really, it doesn't matter what you call it. It's just whatever the bigger function is, that's what goes first, right? So here in this case, the bigger function happened to be that one, 2 minus 2x. The smaller function happened to be this one. And so we took the bigger one minus the smaller one, right? F of x minus g of x. And so when we simplified that, it ended up, like this. Does that make sense? Does that answer your question?
Yes, thank you so much.
Sure. Everybody understand what I mean when I say the bigger function? I just mean the one that has larger y values on the interval. Okay, any other questions before we move on? All right, if not, let's go on to the next thing. So this next problem is kind of just, there's a homework problem on there that just kind of reminds you, hopefully, of the midpoint rule from Calculus 1. There's a few numeric techniques that we used to approximate areas. And this question is kind of like that. So let's take a look at that one. This is example 3 from the worksheet. So this one says, find the, let's see, use the midpoint rule to approximate the area. I'll just try to draw the thing here. All right, so this is, again, example 3 from the 6.1 worksheet. And then they give you several sort of widths marked off here. I'm not going to draw the whole thing, but I'll draw a couple of them to give you the idea of what we're going to do. All right, so it says to use midpoint rule with 2 meter. Let's see. Yeah, so it doesn't even say how many to use. The best way to do this, I think, is to use the midpoint as, from what I have drawn here, the 7.2 width one there. So if we do that, what I'm saying is that we would want to make that the approximate width of the pool, 7.2, on that entire interval. Okay, so basically we're looking at that box right there. See that? And so we want to find the area of that particular box, and that will be 4 meters wide, right? Because each one of those is 2. And then if you look at the picture there, how many can we draw like that? How many rectangles can we draw using that convention? And what would, say, the width of the next one be? Yeah, we can draw 3 of them. Which one would we use as the width for the next one, the next box? 5.6, exactly. And then for the third box, we would use 4.8, exactly. So everybody see that? So basically what we're doing is we're saying that the first box has height 7.2, the second one height 5.6, and the third one height 4.8. All of these have the same width, so we can multiply them all by 4, and then that gives us the approximate area of that pool. So let's do that. So we get 7.2 plus 5.6 plus 4.8, and then times 4, 70.4. that would be square meters would be the units on that. Okay. Any questions on that one? So Michael, it doesn't miss it. It just assumes that the height is going to be 7.2 for that whole 4 meter interval. And then the second one we would assume has a 5.6 meter height all the way for that entire 4 meter interval. You see what I'm doing there? And then the third one would be determined by. So that's a one way to look at it, Michael, but the way that this book is wanting us to do it, trust me, this is the way it needs to be done. We're looking at we're basically determining, we're using 3 rectangles, and we're saying that the height of the first one is determined by its middle, the middle one, 7.2, and then the second one is the middle of that one, which is 5.6. The third one, the middle of that is 4.8. So there are other ways to view this, and I think what you're looking at is probably a different way to view it. However, again, the way that this book particularly wants us to do it is, I think, like this, because this is what produces the answer that WebAssign takes. Okay, so let's go on to the next problem, or the next idea here. So here, this is curves with multiple points of intersection. So what we're looking at here is, suppose that you have a curve, 2 curves, maybe one that does something like that, maybe the other one does something like this. In fact, actually, let me go ahead and use a different color on that one so that we can more easily tell them apart. Suppose I have another function that does something like this. And suppose this is the g of x function, and maybe this is the f of x function. And then suppose that you are asked to find the total enclosed area, which means, well, now you have 2 different regions to look at, right? So what that formula there says is a perfectly fine way to look at this. You can say that that area is going to be just the absolute value of one function minus the other. However, there's more to it than just that. What we have to realize here is that if we do have multiple points of intersection like we do here, then we're going to have to split this up into 2 different integrals. Okay, so perhaps the first point of intersection is at A, and the second one's at B, and the third one is at C. The way that we would view this then would be starting at A and ending at B. And here again, you can, again, just sort of ignore which function is bigger and just take the absolute value. However, the bounds do have to be, oops, and I think I should probably fix that. There should be a C up here, I guess. You can ignore which function is bigger and just put the absolute value on it. Okay, that's fine. Or you can just notice which one is bigger. So like on the interval from A to B, it looks like the f function is bigger. So I would put this, f of x minus g of x. And then I would do a new integral from B to C. And in that case, now the g function is the bigger one. So I would. Okay, so everybody see what's going on there? Any questions about like the setup? Again, it doesn't really matter whether you get these wrong, because you could just say, put the f function first all the time and just say absolute value it. But you definitely do have to split it up, right? You have to find all the points of intersection. You have to go from the first point of intersection to the second, and then the second to the third. That's necessary. So let's take a look at one of those. So this is example 4 on the 6.1 worksheet. We've got one function is cubic. And then you've got another one, quadratic. Okay, so here we would want to, again, to find the points of intersection, you'd set these things equal to each other and solve. So this is going to lead us to a cubic equation, though, so let's see if it's easily solvable. Minus 2x to the third. We've got, let's see, minus 8x squared. We've got plus 6x. And fortunately, those 3's are going to cancel, so that makes this nice. So so it looks like we can factor a 2x out of there, right? And if we do that, we're going to be left with x squared minus 4x plus 6. We do that right? Hold on a second. Let me make sure I'm doing that right.
Plus 3, right?
Well, the 3's would have canceled, I think. Oh, plus 3. You're right. I'm sorry. Yes, you're right. Plus 3. Okay, perfect. So then we can factor that, and we can divide by 2 if we want to. So we get x, and we get x minus 3 and x minus 1. Right, so that gives us x equals 0, x equals 3, and x equals 1. So those are 3 points of intersection. So clearly we're going to have to do this situation where we've got this thing crossing in 2 different places. All right, now the graph. Again, the graphs aren't entirely that important, but they're probably helpful. So let's see, we've got a quadratic with 2x intercepts at 1 and 3. So let's see, 1, 3, and it's opening up. Probably something like this. And then we've got a cubic that has negative leading coefficients. So that means it's going to kind of do, I should probably continue that up there because we're going to have an intersection at 0. All right, so if I plug in 0 to the other one, I get 3. So I guess that one's going to be here. And then if I plug in 1 to that other one, in fact, I don't know. I think I'm just going to have to graph these on my calculator because I can't think about what they're going to look like. Give me a moment. I'm going to put these in my calculator. Okay, and then x squared minus 4. And we probably want to graph this to about 3, so let's see what it looks like. All right, cool. So I guess, if I'm seeing this correctly, the cubic is going to do something like this. So my drawing's not that great, but you can see there's a region right there, right? And then there's another one right there. Everybody see the 2 different regions there? You can graph it on your calculator if you want to get a better look at it. Anyway, so what are we going to do to set this up? The total area will be integral from 0 to 1. That's the first two intersection points. And if you want to put this where the top function is first, according to my drawing, it seems that the quadratic function is first there, so you get x squared, or is the bigger function there, minus the cubic function. Okay, and then simplify that. Well, actually, let's just write the whole thing. So plus, then we're going to have to do another integral, the integral from 1 to 3, where now the cubic function is the bigger function and the quadratic is the smaller one. Or again, it really doesn't matter that, if you don't want to worry about the bigger function here, you're perfectly welcome to just put the cubic one first in both cases, and then whichever answer becomes negative, just make it positive at the end. Because one of them will be negative if you do that, if you don't decide that one of them is a bigger function. Okay, so there's the two integrals that we have to figure out. Obviously not, they're kind of messy there, but let's simplify these. So the first one we're going to get, we do have some like terms, right? Let's just put this in descending order of power. So it looks like we're going to have 2x to the third. Let's see this quadratic term, the second power terms, x squared minus 9x squared, so it's minus 8x squared. And then the first power term is minus 4 plus 10, so that's plus 6x. And then minus, or plus 3 minus 3, so those 3's are going to go away, so we get that. So it simplifies to something a little nicer. And then antiderivative, so raise that to the fourth power, you get 1/2 x to the fourth minus 8/3 x cubed, and then plus 3x squared. Plugging these in from 0 to 1 is nice. If I just plug in 1, I just get 1/2 minus 8/3 plus 3. What is that? 5/6, I guess. And then we got to do the other one as well. So for that other one, we're going to get. So here, if you notice, when the only difference on the integrand itself is that those, the one function is now first, whereas it was second last time. So what's going to happen when we simplify these is everything is just going to end up being negative of what it was before. So we're going to get this. We simplify that. And then we'll plug in or find the antiderivative, same exact antiderivative, so except for the signs are going to be different. So we'll have minus 1/2 x to the fourth plus 8/3 third, and then plus 6x. This time we're going to plug in 1 and 3. See what we get. So antiderivative, same. Now we're just plugging in the number 3, so we're going to get negative. Let's see, if I plug in 3 there, 3 to the fourth is 81, right? That's 81 over 2. And if I plug in 3 there, I get 72. I'll plug in 3 there, I get 18. Now when I plug in 1, I'm going to get minus 1/2 plus 8/3 plus 6. Okay, so let's see what that gives us when I plug all that in together. 124/3, if I did all that correctly. Again, please check me on these things. I do make mistakes occasionally. 124/3. The fact that it's positive, I don't know, that's at least somewhat comforting. So the final answer here is the area is going to be the sum of both of these things. So area is going to be 5/6 plus 124/3. Now let's see what that is. 253/6. I did everything correctly. Did I screw up the antiderivative on that one? Oh, I sure did. I even had it right on the first one there. Sorry about that. Let me fix that. So that should have been, yeah, I had that right on the first part, didn't I? 3x squared. Great. So that's going to change a couple of things, isn't it? Yeah, so that's going to change this 18 to a, let's see, minus, yes, right. If I plug in 3 there, I get 9 to 27, right? So that should be a minus 27, is that correct? And then for this, if I plug in 1 there, that should be minus 3. Is that okay now? Let me fix that. So minus 27 there. And then let's see, 16 thirds. Does that sound better? And 16 thirds plus 5/6, 37/6. Sorry about that. Does that seem better? Okay, any questions on that one? Come on, that one took a while. Okay, this class is supposed to go until 12, what is it, 12:45, is that right? Yeah, so we still have an hour. Okay, so at this point, oh yeah, there's one other thing we need to talk about before I let you try to do some of these. Um, this is something that we have to kind of get used to from here on out. Um, before I go on though, are there any questions on this one? Everybody see how that worked? Okay. If not, I'm going to go ahead and delete this and we'll move on to the next topic. So just I'll use this example 5 as the motivator for this particular topic here. Sometimes we define these functions to be, instead of y equals f of x, we say x equals f of y. So normally it's y equals f of x, and that's like, vertically graphed. But sometimes we graph functions like this, x equals f of y. And when we do that, just you have to remember how that's going to be graphed. And so let's use the number 5 as our example for how that actually works. So let's see. So number 5 says we want to find the area of the region bounded between this function x equals y squared minus 1 and this other function x equals 1 minus y. Okay, so minus 3. Okay, so how do we graph x equals y squared minus 1? kind of function is that? Or what kind of graph does it make? You guys remember that?
Wouldn't it be a parabola on its side?
Yeah, it would be a rightward opening parabola, and that -1 is going to shift it 1 unit to the left. So we're going to have a rightward opening parabola shifted 1 unit to the left. So it's going to look kind of like that. And then y equals 1, or sorry, x equals 1 minus y. The way that you can graph that is by just intercepts. For example, if y is equal to 0, then what's x? Well, if y is 0, x is 1, right? So we could put that point on the graph. That would be the x-intercept of that graph. If x is 0, then y is 1 also, right? If x is 0, then y is 1. So that's the y-intercept of that graph. And since this thing is a linear function, all we need is just those 2 points, right? The x and the y-intercepts, and we can graph it. So that's what the second function is going to look like. Okay, so from here, you can see that clearly they intersect in 2 places. And so the region that we're looking for is right here. That's the region that we want. And then how do we deal with something like this where the functions are defined in this way, x equals f of y? Well, in this case, then with the representative rectangles that we use are going to be these horizontal things. Okay. Now, in this case, the function that is further to the right is the one that's going to be the so-called bigger function. So this one would be maybe our f of y function. Here is the linear function. This one here. And then the g of y function would be the parabola. So the one that's further to the right is now the bigger one, whereas before it was the one that was higher up on the y-axis. All right, so what's the area between these curves then? Well, if we go with what we were just saying about the one that's further to the right is the bigger function, we still need to find the points of intersection here, right? Like, what is that point of intersection there, and what is that one right there? But now we need to find these as y values because we're using horizontal rectangles. So y squared minus 1 equals 1 minus y. Solve that. Y squared plus y minus 2 equals 0. Factor this, we get y minus 1, y plus 2. And so it looks like our points of intersection are at y equals 1 and y equals negative 2. So this y value down here, where those intersect, that's negative 2. This y value up here, that's 1. Okay, any questions about what we're doing so far? So our integral here is going to be lower bound now is the y value of negative 2, and the y value of positive 1 is the upper bound. And then as we said, the function that is further to the right is the bigger function, so that one goes first. So 1 minus y minus the smaller function, which is the quadratic one in this case, y squared minus 1. And then we'll simplify this. So we get negative y squared. Let's see, minus y, and then 2 plus 2. Antiderivative. Okay, and then plug in our bounds and subtract. So we get, plugging in 1 again is nice because we just get the coefficients. So minus 1/3 minus 1/2 plus 2. Plugging in negative 2 there, we're going to get negative 2 to the third is negative 8, so that's going to be 8/3. Plugging in negative 2 there, that's a positive 4. That's going to give us a minus 2 there. And then if I plug in the last one, it's minus 4. Again, please correct me if you see any arithmetic mistakes there. Okay, so I'm just going to put this in my calculator so I don't have to think too much about fractions. So minus 1/3 minus 1/2 plus 2 minus 8/3 plus 2 plus 4. We get 9 halves of that. So the area between those two curves defined in this way, x equals f of y rather than y equals f of x, like this. So I just want to point out on this, this could have also been done with vertical rectangles, but if you want to use vertical rectangles, notice that you would have to solve these things for y, right? That's not that bad for the linear function. Very easy to solve that for y. For the quadratic function, what you would notice is that you would get two different functions, right? Because you'd have to have a positive square root and also a negative square root. So thinking about what that would look like if you used vertical rectangles there, I'm going to come over here and just try to show you in red here. If you were to use vertical rectangles, look at what would have to happen. Think about what those rectangles would look like. There's a representative rectangle right there, right? A vertical one. But if you notice, what is the top bound here? What is the top bound right there? The top bound is the linear function, right? What's the bottom bound? It would have to be the negative radical of that solving this thing for y, right? So basically you get y squared is equal to x plus 1. And so you get y is equal to plus or minus the square root of x plus 1. Right, so this function here, the lower one would be the negative root function. The upper one would be the linear function, right? But notice that if you draw that representative rectangle on a different part, a different area of this region that we're looking at, now look what happened. Now the top function is no longer that linear function, right? Now it's the upper square root function, right? And then the bottom bound would be the lower square root function. So what that's telling us is if we wanted to use vertical rectangles here, we certainly could, but the integrals would be, you'd have to do two of them. For one, you'd have to do the integral from -1 to 0, and then you'd have to do another integral from 0 to whatever this x-intercept point is out here. And the top function in the first integral would be the positive root, and the bottom function would be the negative root. And then if you did it then for the rest of it, the top function would be the linear function, and the bottom would be the negative root. So you can see clearly what's the better way to go here. Leaving it as horizontal rectangles and leaving it as x equals f of y rather than y equals f of x. Okay, so that's the moral here. Often you can switch it back to y equals f of x normal function, but often you don't want to. All right, with this in mind, I do have a couple problems that I would like you to try to work on, although we also technically have to get through 2 sections today, so I'm not going to give you much time. So maybe you can try to work on 1 or 2 of these. I would actually recommend the trig one because, well, I've often found that trigonometry is one of the weak points for calculus students. So let's try to remember our trig. And for now, I'm going to give you a few minutes. Try to work on some of these. Problem 1, you got 3 choices there. Problem 2, that one takes kind of a long time. I typically don't have time to get to that one in class, but if you want to try it, go for it. That might be something that you could, do on your own and maybe ask during office hours or something like that. But for now, again, I would recommend just try that problem 1, maybe part B, because it's got some trig stuff in it. Give those a try. I'm going to give you about 10 minutes to do that. I'm going to go take a little break here, and I will be back. If you do have any questions, Michael should still be in here. You're welcome to talk to each other, talk to Michael, chat, take yourself off mute, write stuff in the chat window, whatever you want to do. But I shall return momentarily. Okay, let's see how we did in one of these. I'll probably only have time to do one of them right now. All right, so let's do that problem 1b. The one that has the trig stuff. So y equals tan x, y equals 2 sine x. And they give us bounds on this one. Okay, so here I would probably want to recommend graphing these. Remember what the tangent function looks like and what the sine function looks like between -pi/3 and pi/3. And remember that the tangent function has a couple of asymptotes on it at negative pi over 2 and at positive pi over 2. But those are not on the region of interest here, so but I just wanted you to remember that they do have those asymptotes there. So here and here. What does the tangent function do otherwise? Well, it just kind of does that kind of thing, right? And then this. Then the sine function that they're giving us, 2 sine x, that's just, well, what does a sine function do between 0 and 2 pi, or pi over 2, pi over 3, I mean? Well, it just kind of does this thing, right? And then it keeps going and sine function thing. So something like that. But again, the region that we're interested in, just this bit right here, and this bit right here. So what we can notice here is that we can actually take advantage of symmetry, because if you look at those two regions that I've shaded in there, what's true about them? True about those two regions. You know, they look to be about equal in size. Yeah, they're definitely the same size, exactly. Because we're going to the negative pi over 3 to positive pi over 3, there's the same numbers but opposite signs. Those regions are going to be identical to each other. So what we can do is take advantage of symmetry and say that the area is going to be twice the integral from 0 to pi over 3. The top function in this case is the sine function, so 2 sine x minus the bottom function is the tangent function. And so you get that. Everybody see what I did with the symmetry there? It just makes it a bit easier to deal with this. Okay, so now we just need to find our antiderivatives. So we're going to get, so what is the antiderivative of sine? You guys remember that? Negative cosine, right? Negative cosine, yep. Now what is the antiderivative of tangent function? We got to remember that. And if you don't remember it, maybe let's do it off to the side here. That's the derivative of the tangent function. We got
1 over, oh, I'm sorry, 1 plus x squared?
Nope. And those are who are saying secant squared. That's not right either, because the derivative of tangent is secant squared, but we're not finding a derivative here. We're finding an antiderivative, right? What is the... Nope, that's not it either. How do you find the antiderivative of the tangent function? Well, probably the best way to do it is by doing a substitution, writing it as sine over cosine. Okay, so if you do that, you write it as sine over cosine, then you can say, let's let u be equal to cosine. And then du is negative sine. And so negative du is sine x dx. Right? And so that means that this then becomes, as a new integral, negative integral du over u. So what's the antiderivative of du over u? Or just 1 over u, right? 1 over u. What is the antiderivative of that?
Natural log of u.
Yes, natural log of u. So we're going to have negative natural log of u, absolute value. But that, and let's forget the plus c here because we're doing a definite integral. So negative natural log of the cosine. But this can actually also be written as the natural log of the secant function. And that's typically the way that we write the antiderivative of the tangent function. You see why we can do the switch it from cosine to secant? It's because of the properties of logarithms. That negative can come up here and become an exponent on cosine. So you have cosine x to the minus 1 power. Well, that's the same as 1 over cosine, right? When you have a negative power like that. And what's 1 over cosine? It's secant, so that's why that works. So anyway, to get back to this, that means that we have minus the natural log of the secant function. I'm not bothering with the absolute value here because, again, these numbers are not negative to begin with, so we're just going to have that. Okay, and then that's going to give us minus 2 cosine pi over 3. What's the cosine of pi over 3? Cosine of pi over 3, what's that?
1/2.
1/2. And then the secant of pi over 3. Two. Yeah, 2. ln 2. And then minus, now here we do have to be careful because plugging in 0 here is going to matter, right? When I plug in 0, what's the cosine of 0? That 1, right? So that's going to be minus 2 there. And then the secant of 0. The heck is the secant of 0? I think it's 1. And when you take the natural log of 1, you get 0, right? And so, okay, so we're going to have, if I distribute that 2 and then distribute it all the way over, I'm going to have 4 minus, let's see, that's going to just be a 1 there, I think. No, actually 2, sorry. 2, and then minus 2 ln 2. So we're going to get overall 2 minus 2 ln 2. And I think something is wrong there because that seems to be a negative number. Let me take a look at this for 1 second here. Does anybody see a problem on that? What is the deal there? It should not be negative. Hold on 1 second. The 4 has a problem? Oh no, never mind. That works. 2 minus 2 ln 2 is not a negative number, so that works. I think that's right. So this is our answer. I forgot the ln 2 is a number that's less than 1, so that works. So unless anybody does see a mistake there, I think that's correct. Okay, any questions on that one? All right, in the interest of time, I'm going to go ahead and move on because we got to get to at least part of the next section. So let's do that. If you do want to do those other ones, feel free, and it's good practice problems for tutoring or office hours or something like that. And in general, we'll try to do as many of these ones that are labeled as problems as we can, but we're probably not going to be able to do all of them. All right, so let's move on to the next section, 6.2.